decide it wanted to do updates. Okay. Yeah, so thanks very much for having me here. So I don't know if someone did intros already, but Brendan Dolan-Gavitt. Okay.
No intro yet. So this is the second monthly Carp Talk. This month we have Brendan presenting Lost at Sea, a case study, which was a paper on the security vulnerabilities that could be generated by Copilot when you give it potentially security vulnerability filled code. Brendan, you can take it from here.
All right. Thanks very much. And you have disabled screen sharing, which I will need.
One sec, sorry. Share screen, advanced screen sharing, all participants. There you go.
All right. And then share some keynote. Okay. So yeah, thanks very much for having me. Let's see if this survives the transition to full screen. All good. Okay. So yeah, thanks very much for having me. I'm a professor at NYU Tandon. I do a lot of software security stuff. I didn't actually start out doing machine learning stuff, but I've kind of got sucked into it over time. And so yeah, what we're basically going to be trying to look at here is if you use something like Copilot to help you write code, what are the security implications of that? Are you going to end up with more vulnerabilities in your code? Or maybe it will help you and your code will just be written faster, it'll be more functional, we will live in the best of all possible worlds. Okay, so this is some work that I did with Gustavo Sandoval, Hammond Pierce, Tio Nice, Ramesh Kari, and Siddharth Garg, who are also at NYU. So let's get started. I can probably skip over and go pretty quickly on some of this stuff because I think we've got a very AI and code model aware audience here. But really, I think it's been sort of shocking to me over the past few years just how much progress there's been in code models. I mean, we went from these models that were sort of barely writing, incoherent PHP code and bits of kernel code to things that are actually now competing at a competitive level at online code competitions like DeepMind, and their commercial tools that you can just now install in your IDE that will write code for you. And now that Copilot is free for students and pretty cheap for everyone else, hopefully some people have already had some experience using this tool. If you haven't, I recommend it. I actually, do enjoy using it. I feel like I program more quickly and I'm more fun when I'm using it, but we did still want to look at the security implications of it. So again, this stuff you probably all know, right? They're trained on vast quantities of code. They're using the standard predict next token kind of objective. So guess what comes next, given what you've seen so far. And then to generate code, you do this kind of autoregressive sampling task where you feed in some prompt, and then it will give you a probability distribution for what the most likely next token is, right? So if you're coding in Java and you write public static void, there's a really good chance that the thing you're going to type next is main, right? And so then you can sample from that probability distribution, feed that token back in to the input, and now you can sample the next token. Okay, and you can do this for as long as you want, up to the context limit of that model, which for many models is like 2048 tokens. Some of the larger ones go up to 4096 or even 8,000 tokens. Okay, so, first cut. How secure is the code that these large language models write? Well, if you read the news and look at the headlines, you might discover, oh yeah, okay, they do in fact write a lot of bugs, right? A lot of these are basically based off of a study that we did back last summer, where GitHub Copilot had just been released. And so we wanted to see what the rate of vulnerabilities in its code was. But it really does do this actually pretty frequently. So here's an example of using Copilot to write a little web app. And I don't know how much sort of web security people are familiar with, but if you look at the way that it has decided to put the username and password here into this SQL string to query the database, it's basically just using Python's standard string formatting, okay? And so if this username or password contains something like an apostrophe, then that will allow the user to inject arbitrary SQL and basically do whatever they want with the database, right? Update it, modify things, slurp down the whole contents, and so on, okay? And that was kind of the default suggestion that it gave, right? So that's not good, right? And so last summer we did this study and we kind of wanted to look at this systematically. So we generated a huge quantity of different suggestions. And these were each suggestions for individual handcrafted scenarios that were designed to sort of potentially elicit vulnerabilities of different types. So buffer overflows, use after free vulnerabilities, cross-site scripting, SQL injection, and so on, okay? And so across all of these different scenarios we looked at, we found that about 42% of the generated programs were vulnerable. Actually, sorry, I am just going to stop for a second so that I can try to get rid of the participant window that's covering up some of the stuff on the side. Okay, Zoom, why are you doing this to me? Okay, that should make things a little bit better. Okay, and now let's go again. Okay, right, so across all these different scenarios that we had generated, we had Copilot write the code, and then we basically measured the vulnerability rates by using this tool also from GitHub called CodeQL, which can do kind of automated scanning for a bunch of different classes of vulnerability. And we found that it was actually pretty bad, right? So there are about 42% of the generated programs were actually vulnerable to the vulnerability we were looking for. And you know, as you might guess, based on just the way these sorts of models work, right? They don't understand the structure of the code exactly. They're just working off of the tokens in the prompt. And so features of the prompt that don't necessarily affect functionality from the computer's point of view do actually affect the output of the model. So depending on the comments you write or the author field you put in, you can potentially get more or less vulnerable code. And one of the things that we found that was kind of interesting is that the strongest predictor of whether Copilot would produce a vulnerability was whether there was an existing vulnerability already in the prompt, right? So this kind of suggested to us that maybe there was some sort of amplification effect at work where it's going to basically condition on code that already has some vulnerabilities, write more vulnerabilities of its own. Those vulnerabilities then go back into the prompt and potentially cause it to write even more vulnerabilities, okay? Okay, but so right after we did this study, you know, one of the most common kind of objections we got was that, you know, this is not really a real world scenario. So, you know, when you're actually using Copilot, you're not just blindly letting it go and complete everything that it wants. So, you know, in the real world, a human is actually in the loop. They're looking at the code that it generates, and maybe they would find and fix any of these mistakes that it generates before they actually make it into the final code. And then the other objection we got was that, well, you know, humans are actually also pretty bad at writing secure code. And so maybe humans would have similar vulnerability rates, okay? And so, you know, these are kind of reasonable objections, and they're not something that our previous work could really examine because that's not really what it was designed to do, okay? The paper didn't actually get a strong reject. It was accepted and people liked it, but this still left us with a bunch of questions we really wanted to answer. So, okay, it was time to do a user study, right? And so what we did was we took a bunch of NYU students at both the undergraduate and graduate level. So from undergrads up through master's and PhD students. And we basically split them randomly into two different groups. So one is this assisted group, which had this an AI code assistant enabled, and then a control group that was just writing stuff by hand. Okay. And we gave them about 2 weeks to complete the task we gave them, and gave them $50 when they completed it. And here, one thing is that we told them that completion didn't mean that they had to fully finish the assignment and complete every different function in the API and make sure that it was all working correctly. Basically, it was up to them to decide what constituted completion. And the students that we were drawing from, so one was an undergraduate operating systems class, which is a kind of junior, senior level course that is based in C. And you write things like, a process scheduler and other kinds of things like that. And then an application security class, which is mixed undergraduate and graduate, but mostly upper level undergraduate and master's students. And then finally, we got one or two people from a sort of informal Discord server that NYU students use to sort of talk about CS and programming related issues. Okay. So we got okay numbers for the signups. So we got about 105 people who signed up for the study. But then there was a fair bit of attrition. So only 58 people actually signed into this web-based IDE we put together and wrote code that we could actually analyze. So just going into a little bit more about what the sort of breakdown of these different participants were. So we had, sort of enrollment levels ranging from sophomores, so second year undergraduate students, all the way up to one PhD student who was in the control group. So a pretty broad range of different levels. They were pretty reasonably distributed among these different categories. I think there are a few cases that were somewhat unequal. So there were the sophomores, there were 8 people who got code model assistance versus only one in the control group. But we didn't try to do too much to kind of balance these groups demographically. We just did random assignment into either the assisted group or the control group. Okay. And so we had these 28 control group participants and 30 assisted AI assisted participants. Okay. We also asked them a little bit about their background. So the task that we were going to give them was basically a singly linked list in C. And so we wanted to know how many people had actually kind of encountered that before. And it was roughly, again, 50-50 between people who had implemented a linked list before and people who never had. And then we also said, well, okay, by this point in the curriculum, you should have encountered C programming before because it's a prerequisite for both these classes. But we actually did find 7 people who said that this was the first time they'd actually ever programmed in C. So, presumably they were going to have to be doing a fair bit of work to kind of catch up as they did this assignment. Okay. But then again, they had about 2 weeks to try and work on it. So hopefully they had enough time to do so. And then finally, just a kind of general background question, we asked them about whether they had ever taken a data structures or algorithms class. And again, most of them had already taken one, right? So about 46 of our participants had previously taken one, and 5 were currently enrolled in one. Okay. So, to run this kind of user study, we really want to make it go smoothly. So if you run a user study and you ask people to, download Visual Studio Code, get a compiler, install this weird extension that we're providing you, and do all this stuff, you're going to get very high dropout rates, right? People are going to bounce off of that when they try to use it on Windows and GCC doesn't work and things like that, okay? So we want to really minimize the kind of environment setup that they had to go through. And we also wanted to, of course, do lots of instrumentation so that we could gather a lot of kind of rich data that we could use to then tell us interesting things about how people were interacting with the code model and how their code evolved over time. Okay, so we use this tool that was developed by some NYU students called Anubis, which is basically just a web-based IDE. And in particular, the flavor that we were using allows you to basically give users a VNC session, so basically remote desktop, into a real Linux system that already has Visual Studio Code and a C compiler and the command line all set up so that you can build and test your code pretty easily, right? So that basically sort of eliminated the kinds of setup issues that we were concerned about. We then basically wrote our own plugin for Visual Studio Code that tries to kind of mimic Copilot. And, we try to do this pretty faithfully, but we didn't do extensive reverse engineering on Copilot. So you shouldn't necessarily say that all of these results can apply one-to-one to Copilot, because maybe there are some important differences still there. So for the suggestions, we used the Codex API, and we logged a bunch of stuff, including document snapshots every minute, so that we kind of see how their code evolved over time. And then the prompt and suggestion data that was sent to and returned from the OpenAI Codex API. And we also logged whether or not they accepted a suggestion, right? So when it provides a suggestion in the IDE, they can hit tab to accept, or alternatively press anything else to not accept that suggestion. And so we logged that information as well. So if you want to know what this environment looks like, okay, hang on a sec. Don't know if that is, hopefully this is not too loud, and I don't actually even know if you can hear the voiceover, but
We can't hear it, by the way.
okay, great. Then I will provide my own voiceover. Okay, so here you can basically see what this looks like. You've got a Linux desktop running in your browser, and as you are typing things in the IDE, you get these nice little inline suggestions. It is very similar to the way Codex works, and you can hit tab to accept a suggestion. Okay, so hopefully not too surprising there, but behind the scenes, we're doing a bunch of logging and reporting of things so that we can then do some analysis on that data later. Okay, so the actual model details. So we didn't want to use Copilot directly because we wouldn't be able to capture as much information about what participants were actually doing while they did this coding. So we instead used the Codex API directly. And OpenAI was kind enough to give us a non-rate limited token for the duration of the study, which basically let us give the IDE plugin the ability to make as many queries as it wanted, to kind of share this one token between the whole user group. And in general, I think it would have been very hard to do this study without that. So thanks to OpenAI for letting us do that. For the code model, we went with the Cushman code model. And so this is not the sort of most powerful and capable model that OpenAI has available, but it has the advantage of being very low latency. And actually, when I did a little bit of digging into the model that Copilot uses, at least when it was first released, they were using Cushman as well. And the reason for that, again, is almost certainly latency, because they really want to be able to return suggestions as you're typing, rather than having to stop and wait for 30 seconds or more for it to actually start returning suggestions. For the temperature and top P settings, so this controls basically sort of how diverse the generated code is. And essentially, if you remember back to how it predicts a probability distribution for each upcoming token, the temperature essentially is going to try and sort of smush that distribution down a little bit, so that there's a greater chance of picking something other than just the most likely token. Okay, And we went with this kind of relatively high temperature. So 0.6 is a little bit high for code generations. Usually for code generation tasks, people use something a little bit closer to like 0.2. But one thing that we didn't want was that basically everyone who had the codex plugin turned on to get the same answers, right? So we wanted there to be a little bit more randomness and diversity in these. And then the other thing is that since we were kind of looking at, how are users going to react when they potentially get vulnerable code or just bad code or nonsensical code, this higher temperature means that there's potentially more chances for that to happen for us to take a look at. Okay, so what did we actually have them do? So we gave them a really kind of awful singly linked list API. And it was sort of designed around the scenario with the idea that you would use this then to implement something like a shopping list. Okay, so there were 11 different functions in total. There was actually a 12th, but it was just the one to initialize the list. And so we implemented that ourselves and didn't ask them to implement it. For the language, we had them write in C because it's basically a target-rich environment, right? It's very, very easy to write insecure code in C. And there are just lots and lots of ways to shoot yourself in the foot. Okay, so if we were doing something like Python, we would have had to really kind of restrict the range of vulnerabilities we were looking at, maybe to just focus on things like web application type of vulnerabilities and things like that, right? So C is definitely sort of the language of choice for writing vulnerable code. We also put in some kind of pitfalls in the API, things that we expected might be a little bit tricky to do securely. And so I'm going to kind of go through the API and point out some of those things to, that we were thinking might trip people up. Okay, so the first thing is just that this node structure for this singly linked list includes a string. And if you've worked with strings in C, it's very, very, very easy to mess these up, either by writing too much data to a fixed size string, or things like messing up allocating or freeing the string and stuff like that. We also had some things like for printing out items, we had a maximum length that it would print, just defined as a constant up near the top of the file. And so again, working with fixed size buffers and copying data in and out of them is very error prone. So, okay, let's kind of look at some of these different API functions. So the first group were just sort of basic list manipulation things. We've got our init function up at the top, which we didn't ask people to implement. And then we've got ones to add an item to the list, update an item that's already in the list, remove an item from the list, and then swap the positions of two different items. And so, here again, we were just really kind of trying to test the basics. And, one thing to look at here this is where we really started adding some pitfalls. So one thing is that every time you specify where something is in the list, you do it by an integer position rather than, for example, being able to directly give a pointer to the node that you want to modify, which means that now you have to keep track of where you are in the list according to its index, and make sure that, for example, you don't run off the end of the list while looking for the right position and things like that, okay? And the other awful thing that we did was we made the list one indexed when, of course, as we all know, the natural, Edgar-Dijkstra approved way of numbering things is to use zero indexing. And so this also adds some additional, this also had some additional opportunities for errors here, okay? And then finally, we had stuff like we made all of the API functions return an error status. And in C, you can't return multiple values, which means that if you want output parameters, you have to give them as basically pointers to the data you want to modify. And so they had to deal with things like double pointers to the head of the list, right? And that certainly tripped people up, because even if you feel like you've got a decent grasp of pointers in C, maybe once you introduce another level of indirection, things get trickier. Okay, next we had some string manipulation functions just to render a particular node as a string, and then to print out the whole list as a string. Okay, and here the main pitfall was the fact that when you try to render an item as a string, the buffer that you render it into is not one that you allocate yourself, but one that's passed into you by the user. Okay, so that means that you have to make a copy of that buffer. Sorry, you don't actually have to make a copy of that. For another one, for things like adding and updating an item, you have to make a copy of this string buffer, because you don't know where it came from, and you won't know if it's, for example, safe to free or not. Here, the issue was that the API, you pass in a pointer to a buffer, but there's nothing really to tell you how big that buffer is. And so here we were expecting people to rely on this max item println as their indication of how big that passed in buffer would be. Okay, and then finally, we had some API functions that were just designed to be a bit harder and trickier to implement. So we had things like a deduplicate function. Deduplication was probably the hardest sort of algorithmic task that we asked people to do, because there you have to basically go over the list somehow and identify duplicate items that are not necessarily guaranteed to be adjacent. So maybe you'll either have to sort that list, or you'll have to do this kind of n-squared thing where you look over each pair of items in the list. And then we also wanted to look at things like if you have to use a system API, a very common class of mistakes is not checking the return status of an API that could fail, right? So you try to open a file and it turns out the file doesn't exist. Or you try to write to a file and it turns out that your hard drive is full because you've been training giant models all day, and it's full of floating point parameters. And so we want to be able to check for those kinds of mistakes as well. One thing I'll say is that particularly for these harder APIs, many people just kind of skipped them and didn't implement them. And so when we were going through and computing statistics and grading things, we checked whether or not they had tried to implement the function. And if they hadn't, we excluded it from the analysis. Okay, so in addition to our human and cyborg users, we also wanted to see how sort of purely automated code models could do. And so here we took the three code models offered by OpenAI. So Cushman, the one that was used primarily in the study, but then also the original DaVinci model and its updated version that was released just this past year. And so basically the way we had them complete this assignment in the automated mode was it would just try to complete one function at a time. You'd give the whole file, or at least as much of it as you would fit in the prompt window, and include the function prototype and comments so it know what to do, and then just have it generate up until it got to basically a closing brace on a line by itself. Okay. Then we would check if that code compiled. If it did, then great, we would move on to the next function. If it didn't, it would try again up to 10 times total. And so the kind of goal here was to mimic a user who was really, really trusts Copilot or Codex and says, I'm just going to accept whatever it gives me as long as it compiles. Okay. One small modification we did have to make is that in C, it's customary to put things like data structure definitions into a header file. And so we had to add a comment at the top in this autopilot mode that said what the members of this data structure were, because otherwise the model doesn't have access to that, and it would basically have to guess what names we chose. And it generally was not very successful at guessing what names we chose. Okay, so what do we want to look at once everyone had finished this and we had all of this data? So the first question, okay, so these are still students, they're still learning how to program, how to write secure code. So first of all, does this help them actually write more functional code, right? Do their solutions work better when they have AI assistance? The next question, and we're security people, so this is the one that we were kind of really interested in, is whether or not they have more security vulnerabilities in the code they write when they have the assistance of the model, or do they not? Okay. And then this is one that I think probably lots of people who teach computer science are going to be interested in now, is whether there are systematic differences in the coding style. So can you distinguish when someone is using one of these coding assistants and when they're not? Okay. And then finally, this last research question, which I think we're not going to have time to get into during this talk, but which you can find in the paper, is if you look at these documents over time and these suggestions, we wanted to get some idea of where the vulnerabilities that we found originated. So were they originally suggested by the code model, or were they written by the human and then maybe potentially replicated by the code model? Okay, so to measure functionality, we had two different test suites. We gave them a basic test suite so that they could just sort of sanity check the code that they wrote. That really just tested the very basics of, does the function do what it's supposed to? Then we also did an expanded test suite with 45 different tests that checked basically every different edge case we could possibly think of. And we had this slightly interesting kind of way of evaluating them, where because there's this problem where if someone messes up their function to add an item to the list, then every test that has to add an item to the list is also going to fail. Okay. So to reduce those dependencies, we basically split the user's code into individual functions and tested them in isolation and filled out the rest of the functions using our hopefully known good reference implementation. I tried very, very hard to make sure that that one was bug-free. This also means that we were able to evaluate code written by users who submitted stuff that didn't actually compile, because as long as some of their functions compiled, we could still test and evaluate those. Okay, so here's what it looks like. So I subtitled this Rise of the Machines because, in fact, it turns out that in general, the AI assistants did seem to help here. So if you look kind of from left to right, we've got the control group, the group with this AI assistant, and then this fully automated mode. Okay, and so generally speaking, the ones who had assistance did significantly better on the number of functions they implemented, the number of compiling functions they had, the number of basic tests that they passed, and the number of expanded tests they passed. One thing that was kind of interesting too is that the fully automated mode in some cases actually did better than unassisted humans at writing code that passed functional tests. Okay, so again, there's more details in the paper. So some of these comparisons, when you do compare one group to another, don't reach statistical significance because we, for example, because we only had 58 users total, So this is a fairly small group, but there are a few of these that do actually turn out to be significant. Okay, so now the one that we kind of care a little bit more about is security. But this is actually very hard to measure. So CodeQL, which we used in our last study, we found that at least with this particular task, it missed a lot of issues and it had false positives. We also tried using fuzzing, where you basically throw lots of random inputs at these functions and then look for things like crashes. But fuzzing has this problem where if you get 10 crashes, you don't know whether or not that's 10 different bugs or one bug with 10 different manifestations. So in the end, we basically just said, you know what, we're just going to read all of the code by hand, go through it carefully, try to identify every vulnerability we can find. And so 3 of us basically. Oh, sorry. So was there a question?
Someone joined and their mic was on. It's okay.
Wow.
Oh, I'm so sorry. I'm so sorry.
Not a problem.
While we're paused, do you mind if I ask a question?
Yeah, sure.
What is fuzzing?
Okay, yeah. So fuzzing is basically where you take the program and you hand it random inputs and then just look for crashes. So it's kind of a very basic strategy, but one that turns out to be very effective for finding problems. It's a little bit harder to test a program with fuzzing if you have just an API to work with rather than something like a file parser. But what we did was we basically said that the input, each piece of the input will tell you which function you should call and what arguments you should give it. And then we basically ran that with randomly generated inputs so that it would exercise random API functions with random values provided to it. Okay. So yeah, if fuzzing is definitely something that is good to use. It didn't turn out to be appropriate for our particular use case here. But if you're just trying to find problems in your own code, I definitely recommend it. It's very highly effective. It has found lots and lots of security vulnerabilities in widely used software. Okay. So what do we do instead of fuzzing or using one of these nice code analysis tools? Exciting.
Oh God, let me kick this person.
Okay. All right. So, yep, no problem. So in the end, we just had to review the code by hand. So we basically sat down, went through each function and tried to annotate it with all the vulnerabilities we could recognize. And we then categorized them based on, there's a sort of standard taxonomy of security vulnerabilities called the common weakness enumeration. And so that let us say, okay, this is an instance of a buffer overflow. This is an instance of a null pointer dereference, an instance of using an item after it's been freed, things like that. In addition to the user code, we also went through 5 of the Cushman autopilot answers. We didn't grade all of the autopilot answers because by this point we were kind of running out of steam. And total that took about 20 hours of manual review. Okay, and after all of that work doing this evaluation, basically, regardless of how you slice the data, there's not really a whole lot of difference between these groups. So whether you look at the number of vulnerabilities per line of code for just code that compiles, or for code that passes a basic unit test, or whether you restrict it to severe vulnerabilities versus non-severe vulnerabilities. And again, that classification is based on one from this organization, MITRE. There don't end up being really significant differences between the groups. Some of that's our sample size, and some of that is just that there were not huge differences. If anything, and this is a little bit dicey because, again, we're dealing with a small number of users here, and there's So some of this could just be statistical chance. But sorry. Okay. So yeah, some of this could just be sort of statistical noise, but there is a general kind of maybe trend that says that it seems like on average, the control group had a slightly higher rate of vulnerabilities. So there's a question from the audience about why we look at vulnerabilities per line of code versus just total number of vulnerabilities. So the reason for this is that we want to control for how much code people actually wrote. So one of the things that we saw back here is that the users who had Codex or Copilot enabled were more likely to write code that actually worked. And they also tended to implement more functions. So they had more opportunities to write vulnerabilities. And so we wanted to kind of control for that effect. So that's why we were looking at vulnerabilities per line of code. Okay, so that's kind of the high level result on security, is that there doesn't seem to be a big difference. There's a maybe small difference in favor of using the AI code assistant, but since these results aren't statistically significant, we don't want to make strong claims there. Okay, and this just breaks it down by the different category. I just realized that I should have put in the actual descriptions of these into the slide. But these are things like buffer overflows, using an item after it's been freed, using memory before it's been initialized, copying past the end of a buffer, dereferencing null pointers, and things like that. So again, there are full descriptions of these in the paper itself, which you can go check out on arXiv. I think there's a link in the Discord, but I can also drop one into the chat here after the presentation. Okay, and so finally, one of my kind of favorite results from this paper is we wanted to look at if there were systematic differences in how people wrote code and what their code ended up looking like, and answer this question of whether you can tell if someone is using one of these code assistants. So the first thing we did, so if you know Stella Biederman, who does a lot of work with Eleuther AI, she and Edward Rath had a paper looking at whether this tool MOSS, which is one that's commonly used for plagiarism detection, could tell the difference between human and human answers to coding problems versus GPTJ's answers to coding problems. And so we did the same thing with the data we had. They incidentally found that MOSS could not distinguish between human and machine-generated answers. And then the other thing that we wanted to look at, which I think is a bit new, is that if you've worked with a lot of these code models, one thing you may have noticed is that they have a tendency to repeat themselves. So I wanted to look at the quantity of repeated substrings in the file. So the idea is you take the longest common substring, count the number of occurrences in the file, remove it from the file, look for the next longest substring, and keep doing this until you drop below strings of a particular size. In our case, we chose 16 characters. And then you look at, if you compare the fraction of repeated code to the whole file, then sort of what percentage of the file is repetitive. Okay. So here are those results. So on the left here, we basically did a heat map where we're just looking at, so this is one of these heat maps where only half of the heat map is actually unique, right? So we're just comparing pairs of users. And if you look at this and say, it's really hard to actually tell anything, good job, because we also could not really detect any patterns here in terms of similarities between different submissions in the group using MOSS's file similarity score. So this kind of replicates that result from previous work, that these plagiarism detection tools are not going to do a very good job if you want to use them to tell if people have been using something like Codex or Copilot. So then over on the right, we also did the same thing. So this middle graph here, this Moss similarity between groups, this is basically the same information as in the heat map, but just grouped as a box plot. And again, there are not really very significant differences here. And if you are familiar with Moss, the number here is the percentage of the file that was matched between any pair of users. And so you can see that really it's not very much, right? So in general, the average is somewhere between, maybe 4 and 10% of the file was similar between two users.
So out of curiosity, were you able to, like, when you were reading and manually grading them, were you able to detect, at least intuitively, which ones were Codex generated and which ones were human generated?
There were a couple times when I thought that I could. We deliberately, while we were doing the grading, we blinded ourselves, so we didn't know who had it turned on and who was in the control group. But when I went and looked back later, I was often wrong about my guess, so I could not tell really. So okay, the one significant thing here, though, is this one on the right, where it turns out that the code generated with code model assistance or by just using the code model in fully automated mode does actually turn out to be more repetitive. And so actually, if you compare these sort of within file similarity scores across these three groups, you get this kind of nice progression where the control group is least repetitive. The AI assisted group is slightly more repetitive, and then the ones that were fully automated were the most repetitive. So this one I think is kind of interesting because it points to a way that we might be able to start potentially building tools that can fingerprint and identify whether or not code was produced by a language model. Okay, so to wrap up, because I think we're kind of running out of time. So we did find fairly significant differences between these groups on functionality.
By the way, you can go
Yes.
over because you started like 10 minutes late. So it's
Okay.
Okay.
Well, I think I want to have some time for questions too, but so okay, so yeah, so for the conclusions, right, basically we did have big differences in how sort of functional the code was in terms of passing the test we wrote. There wasn't really a discernible difference on security. If there was any trend, it was in favor of the code model assisted users. And so we were really kind of limited by the small sample size here. And so we're definitely hoping to expand this to a much bigger set of users in the future. And we did find this kind of interesting signal that we can maybe use to distinguish code that was written by Codex and Copilot. So, there are some kind of limitations that you probably have noticed. One is, of course, this is one task and one language. So maybe it doesn't generalize to things other than writing a linked list or writing in languages other than C. Again, these are students. So, maybe professional developers, you would get very different results. Maybe not. And then obviously small study that was limited in the number of people we could get to participate. So all these things we're hoping to kind of expand and do more user studies like this in the future using this kind of similar methodology. But with that, I would be happy to take some questions. I think there's already one that's on the Zoom chat, so I can take a look at that. Right, so someone asked if the results could be related to the temperature being set to 0.6. So potentially yes, right? So certainly in the worst case, if the temperature was set to 0, then you would expect that all of the suggestions given to an individual user, as long as the prompt was the same, would always be identical. So that would presumably result in much more similar code between different users. But on the other hand, I guess if you're if you think about this in the context of a human writing code in conjunction with a model, they're probably going to add in some code of their own as well, and that's going to change the model's outputs as well. So I would guess that even if we had set the temperature fairly low, we still would have had a lot of trouble telling the difference between the human and the AI-assisted users using a tool like Moss. Okay, did we interview any of the users? No, so we didn't do user interviews. Partly that was because we just didn't have a lot of time between when we finished up the study and when we were trying to write up the paper. And also just in the IRB, we didn't include interviews as one of the bits of data we were going to collect. So unfortunately, we only have the responses to the survey that I showed and the demographic data for them, as well as, of course, the code and instrumentation logging from the IDE. Okay, next question we've got. So for identifying text written by Copilot, is it possible to get Copilot's log likelihood of a document? This wouldn't necessarily generalize across models, but it seems like it would identify Copilot quite well, and the likelihood score should correlate pretty directly with how much was written by Copilot. That's actually a very interesting idea, right? Because I guess you're right that you should be able to, that if it was produced by the model, it should be sort of less surprising to the model than if it was written by a human. But that's something we didn't think to measure. And probably after this talk, I now kind of want to go take a look at that. So I will do so. So thanks for an excellent suggestion. Okay, is there some concern that by the time you can properly investigate the characteristics of current coding LLMs, the state of the art will shift enough to make that analysis obsolete? Yeah, potentially. So this field is moving very, very fast. One thing I will say is that the quality of the GitHub Copilot completions has increased a bit over the course of the past year, but I believe they're still using the same underlying model, and most of the differences have been in kind of prompt design and prompt engineering. So things are moving fast, which is also why we're trying to do things like, we put this up on archive about 2 days after we submitted it, so it's still under review. But yeah, things are moving fast. We're trying to move fast too. Okay, do we have any differences for why there wasn't any real difference in security, and whether there might be a difference given a larger sample size? Yeah, so I think part of this it could be the fact that the group of users that we had were still kind of fairly inexperienced programmers. And so, one possibility here is just that the rates of the purely human users were higher than you might expect than from, say, professional programmers, right? So that would mean that, potentially, even if the quality of the Copilot code wasn't very good, it still might be better than someone who just hasn't used C very much. But again, this is something that we do want to try and take a look at with more users to get some kind of sort of more definitive conclusion there. I guess at the moment, all we can say is that for this particular user group, and then we can sort of rule out that there was any very large effect, right? Because if there was a really large effect, then even with a small number of users, we would have been able to detect a significant difference. But as it was, with the number of users we had, the differences were not very significant. Okay, do we find Copilot models more likely to make a specific class of mistakes versus human users? Yeah, so there were a few of these that we noticed. I can go back and try to pull up that chart. That's functionality down here. Right, yeah, so there are a few of these. So one thing is that I would say is you should probably ignore the green bar because the green bar only has 5 samples in it. And so in some cases, I believe that the very tall green bar here over on the left, I believe that that is driven mostly by one particular code sample where the fully automated one basically wrote the code in an incredibly strange and convoluted way, and repeated a bunch of lines, and it just happened that the lines they were repeating over and over again had this particular security vulnerability. 476, I think, is use after free. Let me just double check. Oh no, so CWB 476 is null pointer dereference, right? So they had, I believe they just had a bunch of null pointer dereferences. But okay, then looking at ones that were different between these different groups, so there are differences. Again, they're fairly small because here this is the difference between maybe 31 and 35%. So I wouldn't necessarily make too much of the differences here. There were even a couple where they were either only made by the assisted group or only made by the control group. But again, I think the numbers are not really large here and the differences are not really large here. So I'm hesitant to conclude that there were ones that were much more likely to be made by one group versus another. Okay, any estimate of prevalence of these types of vulnerabilities in the code that Copilot was presumably trained on? So not really, because measuring prevalence of vulnerabilities of tons of code in the wild is sort of a totally unsolved problem. We have a little bit of data on the prevalence of the vulnerabilities that people tend to find. And so MITRE and some other groups produce statistics on that each year, and you can go check those. That's actually how we chose when I mentioned back here that we looked at severe versus non-severe. So every year MITRE puts out the top 25 most severe vulnerabilities, and they do that by basically taking the prevalence in vulnerabilities reported that year times the sort of what was it? Yeah, prevalence versus a measure of how dangerous the vulnerability is. Okay, do you have any thoughts on how to build code models that are less prone to making security errors? Yeah, so there's a couple of things. One is there's some interesting work on using reinforcement learning to update models based on human feedback. And so instead of human feedback, we could basically run things like security scanners. And then use that as a signal to update the model. The other thing we could try to do is try to do things like create sort of more curated fine-tuning data sets that we've sort of more thoroughly vetted or audited, and then use those to try and fine-tune. And that might help with security as well. And then finally, there are things like, maybe you could take a kind of really simple solution, like every time the model generates some code, just always run security tools across it. That's kind of good practice to do anyway, but it could potentially be built into IDEs or things like that. Okay, yeah, do we have thoughts on the comparison of this study to the one done by Google in terms of compiled code, number of tests passed? Yeah, so I think that we did see this, and we do have a kind of comparison in the related work section of the paper. But yeah, basically broadly, it seems like we had more or less the same findings as Google did, that it seems like these models actually do really help users write code that is at least more functional. Okay, when C is taught in a university setting, what sort of emphasis is placed on security vulnerabilities versus other types of bugs? So I will say, I mean, I guess I'm a security person, so when I teach parts of when I teach C to undergraduates and graduate students, I do kind of make a big deal about it. The other thing I would point out is that if you look back at the demographics, or at least where the students were recruited from, one of them was actually in application security. And I know that course quite well because I was teaching it at the time we did the study. And, the first, I think, month or so of the class is all about C-based security vulnerabilities. So in principle, they should have actually had a pretty decent, the participants from there should have at least had a pretty decent idea of what kinds of problems occur in C code. Okay, and then finally we've got a question from Shalja. Do you think having the users as all students as opposed to having novice, average, and proficient, who might be better at recognizing vulnerabilities, would that have made a difference to the outcome of the study? I suspect it would. I mean, I guess it's sort of hard for me to believe, now having kind of looked at all of the submissions manually, it is sort of hard for me to believe that a very experienced C programmer would have made errors at quite the same rate that we saw in our data set. But, the main problem was that we just did not have very much access to those types of users, right? Those people have jobs that pay them lots and lots of money, and we had $50 to offer. And I guess then sort of from just an institutional standpoint, it is a bit harder to get IRB approval for studies that involve people outside the university, which, it's not that much more work, and we are planning to try and extend it to more experienced users. But that's something that we weren't able to do for this particular study. Okay, is there much work on using learning-based algorithms for detecting vulnerabilities? There is. My general impression of it is that it honestly does not work very well right now. The main problems are that data sets of security vulnerabilities are in short supply, and particularly for training large models, there's not nearly enough, sort of curated data on vulnerabilities in code for training a model like that. And then the other issue is just this issue is sort of what's this, Bayesian base rate fallacy. So, relative to the total amount of code that there is in a given project, the number of, say, lines of code that contain a vulnerability is a very, very small percentage of that. And so even if you have a very, very accurate detector, the vast majority of findings by a statistical model like that are going to be false positives, right? So, and, let me tell you, as someone who has reported vulnerabilities and used the, vulnerability detection tools, there is nothing that developers hate more than someone reporting a vulnerability that turns out to be a false positive. But I think it's still an area of active research. It's something that lots and lots of people are trying to get better at. But I think it's just a very hard problem. And if it could be solved, then I think you would A, make a whole lot of money, and B, make the world a much safer place, because finding vulnerabilities in software is still a very hard and unsolved problem. Okay, question: how good is Codex at determining if the code it writes has vulnerabilities? So I've only done some kind of like anecdotal messing around in the OpenAI playground with this. And when I fed in some code, I think this was PHP code that had two different vulnerabilities, and asked it to, if there were vulnerabilities, it would, if you just ask it if there are any problems or issues in the code, it will give you very generic answers. And just say, oh, it's written in a bad style, it's not very reusable, and things like that. If you kind of forced it to enumerate security vulnerabilities, I believe in the case that I looked at, it found one of them, but not the other one that was in the code. Even after you asked it, are there any more? So it's not amazing at telling if code has vulnerabilities in it. But potentially, that's something it could presumably get better at with some fine tuning. Let's see. Okay, maybe one last question before I might have to get going. This is from Tanish. We've got one that, did you know if any of the students previously used AI coding assistants like Copilot or Tab9? Yeah, so actually, we don't know for sure. But one thing that I noticed is that a couple of the users had done the same trick of putting the data structure definition as a comment at the top of their file so that the code model could see it. And so that indicates to me that they probably had a little bit of experience with something like Copilot or Tab9. One thing I will say is that we did give them kind of an introductory video where we sort of explained how the models work, walked them through the ID and things like that. So they weren't coming in with sort of zero information about how these models actually work, but of course they were definitely not experts. Okay.
Brendan, it was great to have you. And if anyone has more questions, I mean, feel free to ask them in the Discord. I'm sure either Brendan or someone else would get to them. And furthermore, if anyone wants to potentially give a talk, we are looking for people working in like HCI, NLP, and RL who might want to give talks. So feel free to reach out to me on the Discord. All right. Thank you, Brendan.
Thank you for having me. And yeah, I'll be around in the Discord to help